seconds, and frequency is 1 over seconds. So what is a joule? A joule is a unit of energy, and it's super cool. There's this guy named James Prescott Joule, and he got knighted for his work, and he proved that the energy that chemists use, and the energy that physicists use, and the energy that biologists use, they're all the same. He proved that energy is energy is energy is energy. It's all the same. Whether it's chemical energy, biochemical energy, mechanical energy, electrical energy, it's all the same. So the joule is named for him. Joule is the SI unit of energy. It's a very, very, very small amount. Like right now, you're basically burning hundreds of joules per second by just thinking about it. But anyway, so that's the unit of energy. Kind of cool. All right, questions? So each photon of green light is carrying a tiny, tiny, tiny 4 times 10 to the negative 19 joules of energy. Not very much. In fact, violet light would only carry about twice as much energy per photon. But, so 1 photon, not a big deal. A lot of photons, that's a big deal. So if you get hit with 1 ultraviolet photon, you're going to be fine. If you get hit with hundreds of billions of ultraviolet photons over a long amount of time, you're going to get a sunburn. And 1 violet light photon won't do much. But in my laser, we're firing hundreds of thousands of them at one point, and it makes this. Yeah. Good point, yo. So that's the, so now you know how to find the energy per photon of a photon. Okay. Give me a thumbs up if you understand what just happened. Wave your hand around if you want me to go over it again. And we're moving on. Okay. 3 questions. I want you and your neighbor to discuss these 3 questions. Take a minute or 2. And of ultraviolet, which is slightly higher in energy than visible, and infrared, which is slightly lower in energy than visible, answer these 3 questions.
No, that was a joke. I love that one.
Okay. Ultraviolet and infrared. Ultraviolet is above violet, higher energy than violet. Infrared is below red, lower energy than red. Of those 2, if you believe ultraviolet has a larger wavelength, raise your hand. If you believe infrared has a larger wavelength, raise your hand. You are right. Infrared does have a longer wavelength. Frequency. If you believe ultraviolet has a higher frequency, raise your hand. If you believe infrared has a higher frequency, raise your hand. Oh, good. Yep, it's ultraviolet. Ultraviolet has a higher frequency. And if you believe ultraviolet moves faster than infrared, raise your hand. If you believe infrared moves faster than ultraviolet, raise your hand. Good. They move at the same speed, right? Yeah, good. Because they're both electromagnetic radiation. All right. I still haven't got through your guys' all your cards, but last year somebody asked on their card, they asked, how does digital photography work? How does the camera on my phone work? Anyone know how the camera on your phone works?
No.
Magic, yeah, it's enchanted. Accio telephotography. Okay, so about between 200 and, let's say 20, between 200 years ago and 20 years ago, we had this idea where there was this thin film of plastic, or acetate, depending on what generation we're talking about. And on this thin film was this layer of silver compound. Do any of you have transition lenses that change color when you go outside? They get darker? Okay, so if you have those, they get darker when you go outside, you have the same chemical we used in photography for 200 years. So what happens is the silver, when it's exposed to visible light, turns black. And what we do is we have a shutter and we go open, close, and a little bit of light would strike the film, and where the light struck the film, those silver compounds would come out, change a little bit, and turn dark. And the more light that hits it, the darker it would be. Make sense? And then that would produce a negative, where light things were dark, then you basically shine light through that negative, and dark things turn light, and you get an image. That's how it's been for about 200 years. But we don't use that anymore. I don't know anybody who uses film anymore. What we use now is a sensor. So digital photography uses a sensor that can pick up blue light, green light, or red light. And there's all these tiny little sensors, and they're crammed into a tiny circuit board, so small that a human can't make them. They have to be made by a computer with lasers. Computers are making computers. And there's a green sensor, a blue sensor, and a red sensor. And for one dot, it picks up, okay, I picked up 1,000 red flashes, 1,000 red photons. I picked up 2,000 green photons and 2,000 blue photons. I'm going to call that dot cyan. And then another one next to it says, oh, I picked up no red photons, 1,000 green photons, and no blue photons. I'm going to call that dot green. And that's how it works. It's kind of like playing Battleship, where it's like A or bingo. Like A1 had this many dots of this many dots of this, so we're going to call it that color. A2, call it that color. And inside your phone, there's a little gnome who writes down how much green, red, and blue hit the sensor, and then they say, and then he reads that off to the computer and says, okay, there's 256 parts of red, 256 parts of blue, and 256 parts of white, or of green. So somebody says, okay, that's white, and makes a white dot on your screen. That's how it works. That's digital photography. So this functions at the chemical level, this functions at the quantum level. Photons come in, electrons come out, and those electrons go to a little circuit board, and it reads it as different amounts of red, green, and blue. Kind of fun. I think it's kind of fun. Anyone ever done any web design where you look at color coding? It's like 256, 0, just 3 numbers. That's what it's talking about. How much blue you have, how much red you have, how much green you have, and that corresponds to a color. Yeah. Okay, ready to move on? Any questions before we move on? Then we're moving on. All right. So, green is not a creative color. So, when electrons gain energy, guys, when electrons gain energy, what do? They jump up and get excited. Do they stay there for a long time? No. They come back down. And here's the cool thing. Since every atom of every element has a unique combination of levels, every atom has a unique quantum fingerprint. It's called the emission spectrum. This is the emission spectrum for hydrogen. So that one electron can jump to multiple levels, and each of those jumps, as it falls down, produces a band of light. Capiche? So every atom, because they have a different number of electrons, different combinations of jumps, they all have a unique fingerprint. This is the one for hydrogen. So this red light might be a jump from level 6 to level 5. Very small jump. This green light, these green bands, they might be jumps from level 4 to level 3. I'm sorry, level 4 to level 1. Medium-sized jump. And these blue and violet bands, these might be a jump from level 7 down to level 1. Big jump. Big jump, violet, medium jump, green, yellow, and small jump, red. This is the emission spectrum. This is how we know that what comes out of stars. So we don't go out there with a giant scoop and scoop up what comes out of the stars. What we do is we look at the plasma that gets launched out of the sun and say, ah, that's giving us these bands, that's oxygen. It's giving us these bands, that's boron. That's giving us these bands, that's aluminum in the plasma. It's pretty neat. Okay. Moving on. So again, every element has a unique fingerprint based on the number of jumps and falls that can happen in the bands because of those jumps and falls. Okay, so here's a couple of them. This is actually really neat. If you want to see the bright line spectrum from a lot of elements, you can go to Web Elements. This is one of my favorite. This is sodium. You're going to investigate sodium tomorrow in lab. With fire. One of the few labs where we actually have like large open flames. So if you don't have a scrunchie, Alex, if you don't have a scrunchie, make sure you bring one tomorrow. So yeah, so sodium has a bunch of blue bands right here. By the way, this is flipped over. Now high energy's on this side. I wish I could find it. I wish it wasn't this way, but it is. So blue's right here, red's on the other end. So we got a bunch of blue bands, some green bands, some yellow and orange, and some red bands. Sodium is cool because of where they use it. Sodium has very significant green and yellow bands. Does anyone know where sodium lights are used? Where they use the vapored sodium in light bulbs? Street lamps. Old street lamps use sodium vapor. So those old street lamps, if you look, it's like, ew, it's all yellow. That's because of the sodium. And then another favorite of mine, mercury. Mercury has 80 electrons and thousands of bands. Bunch of red bands here, bunch of blue bands here, some green, some yellow. Mercury, when you heat it up and shine light through it, so it's vapor, it makes a brilliant white color. You know where you use mercury vapor lamps? Gymnasiums and stadiums. They're right up there. So there's a couple hundred of them outside, and they use mercury lights. So basically, the electricity goes to the mercury, it vaporizes the mercury, and the mercury gets vaporized enough and hot enough it starts to glow. Which is why you're in the gymnasium with the lights are on. If you turn your lights off and turn them on, they don't come on right away. They have to warm up. So yeah, they use them outside in the gymnasiums because if the lights break, we're like, okay, you guys can go. They don't use them in here, because they use them in here, and when the lights broke, we'd be like, well, we can't use that classroom for a couple weeks. But in the gymnasium, they just like, okay, everybody evacuate and blow the air out. It'll be fine. And if it's outside, we just ignore it. Okay, so that was emission spectrum. Is emission absorbing energy or giving off energy? Giving off. Absorption is taking in. We have never been, or at least, okay, we have actually recently, but we knew what Neptune was made out of long before we ever sent a satellite there, or a spacecraft. Long before we sent Voyager, which is what it was called, long before we sent Voyager there, we knew what Neptune was made out of. Anyone have any idea why? Or how? It has something to do with spectrum. I'm going to say absorption spectrum. What color are all stars? White. We established that yesterday, right? All stars are white. Okay, so what we do is we look at a star, way over there. Hey, there's a star. We're going to look at that star. And then as Neptune moves in front of that star, something kind of interesting happens. We would normally see all the colors of light coming from that white star. But as light travels through Neptune's atmosphere, some light disappears. And that's the absorption spectrum. The gases in Neptune are absorbing the energy of certain wavelengths of light. And that certain wavelength of light, we can say, oh, based on what's not there, these are the chemicals that make up Neptune. So we would normally see all of them, but based on what is not there, we can look at, we can know what gases make up Neptune. So this is the absorption spectrum of hydrogen. This is what happens if you shine white light through hydrogen. Hydrogen will absorb certain bands of light, and the rest of them you'll see. The absorption and the emission spectrum are basically opposites of each other. It's kind of cool. It's also how we know what Venus was made out of, even though we've never like scooped up some Venus. Yeah.
So the spaces, those are the ones that get absorbed?
Yes. Yep. The gas that we don't see is where the gases have absorbed energy. So we see what's not there, and we're like, based on what's not there, this is what's absorbing the energy. So far so good? All right. We're about to take a turn. So I want to make sure you're comfortable with this stuff before we make a turn. All right. So Bohr came along, he says, no, the electrons are not all in one shell, they're not in a cloud, they are in multiple shells. And I printed up those atoms for this purpose. Those of you who have an atom model, in the very first shell, how many electrons do you see? Two? Two? Yeah. So depending on if you have something really big like gold or really small like oxygen or phosphorus, there should only be 2 electrons in the first shell. The first shell has 2 electrons. So the first of Bohr's shell has 2 electrons, or can hold up to 2 electrons. Now, follow the crazy out of focus blue or green light to the crazy green light. Follow the green light to the wall, and you'll find the first row of atoms. In the first row of atoms, how many atoms are there? 2. There are hydrogen and helium. 2 atoms in the first row. How many electrons in the first shell? 2. Those of you who have models, how many electrons in the second shell? 8. There are 8 electrons in the second shell. Back to the periodic table. How many atoms are in the second row? 8. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 atoms in the second shell. Wow. Okay, if I drop it more times, we can come back into focus. Anyway, 8 atoms in the second shell. Second level, in the second row. This is not a coincidence. The the 2 electrons in that first shell are so low in energy they can only have the hydrogen and helium. That shell is so low in energy it can only hold 2 electrons. The second shell is higher in energy, it can hold 8. And here's the really weird part. Those of you who have models, how many electrons in the third shell? 18. So the third shell can hold 18. And those of you who have gold and silver, you can actually count how many is in the fourth shell.
18.
Yours only has 5? Oh, in that last shell. In the last shell there's only 5, yeah. Because you haven't filled that shell. 32. Yeah. All shells after shell 3 can hold 32. So it's 8, 8, it's 2, 8, 18, 32. Now, very few atoms actually hold all 32. Especially the ones that I printed. The biggest one I printed was gold. But that's how it works. Okay, so let's go back to the periodic table. Are you paying attention to the periodic table? Shell, energy level 1. By the way, if you call it energy level, great. If you call it shell, great. If you call it energy shell, great. Whatever. So, energy level 1 has 2 electrons. How many atoms in row number 1? 2. Energy shell 2 has how many electrons? 8. How many atoms in row 2? 8. Energy shell 3 has how many electrons? 18. How many atoms in row 3? See what I did? Whoop. Whoop. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Mr. Byers, those are not lined up with the row. Yes, they're not. This row of 10 right here is actually in the third row. But it's moved down. That's the mystery. We'll solve the mystery on Thursday. On Thursday, I'll tell you why it is that scandium through zinc are actually pushed down one row, but they are part of the third shell.
That's
Very weird. And it makes a lot of sense when you figure it out. And I'll solve that mystery on Thursday. Okay, questions? All right. So if you understand the whole shells, these are the biggest buckets of energy. Shell 1 has a very small bucket of energy. It can only hold 2 electrons. Shell 2 is a little bit bigger. It's a bigger bucket of energy. It can hold 18 electrons. Shell 3 is an even bigger bucket of energy. It can hold 18. And shells 4 through 7 are bins of energy that can hold 32 electrons each. Now, within those shells, you have things called orbitals. Okay. As a math teacher, at the elementary level, you have to teach kids that 4 divided by 3 is 1 remainder 1. Remember that? Remember remainders? 1 remainder 1. Then you said, oh, 4 divided by 3 is 1 1/3. Then you said 1.3, then you just go off. Well, I'm going to teach you where you should be at the high school level in chemistry. At the high school level in chemistry, electrons are packets of energy and they travel around the atom. In about 3 or 4 years, if you stick with physical chemistry or physical science in general, you'll learn that that's not quite the case. Electrons aren't really things, and they don't really travel in paths like cars and people, but it works, the analogy or the model works well for us. So an orbital is the path in our model that an electron travels as it travels around or through the atom. It's called an orbital, kind of like in orbit. You know, the Earth orbits the sun, the moon orbits the Earth, and so on. So an electron orbits the nucleus, so we say an orbital is the path that it travels. These create shapes of very significant signs, and this is what I made this morning. I made a dice with various orbitals on it for the game we're going to play this week that I invented this morning. On my way here. The simplest shape. Oh, before we talk about that, each shape, each orbital can hold 2 electrons. Kind of like your